大家好，欢迎回到电磁理论。In this set of slides, we are looking into boundary conditions. That is the description of electrical field and magnetic field on the interface of two different material, which means the two material have their own electromagnetic properties. We know that there are only three electromagnetic properties: the permittivity, epsilon, the permeability, mu, and the conductivity, sigma. So as you can see in the top right corner, we have material 1 and material 2. They have their own electromagnetic properties, material property, epsilon 1, mu 1, sigma 1, epsilon 2, mu 2, sigma 2. And the interface is not necessarily a planar surface. It can be a curvature, like what we see here. So down below is material 1, above is material 2, and it's a curvature. So we try to determine the relationship of E and H field above and below the interface. And here we have current Ji, the impressed current density, flowing on the surface. Okay, flowing on the surface. So it's remarked with a red arrow. In fact, the red arrow should be pointing perpendicular. Here the blue rectangle indicates the space, the region we are interested. As you can see, there are focus on the interface between medium 1 and medium 2. The red arrow, the impressed current density, is actually the currents passing through the blue rectangle. They should be normal to the blue rectangle. 也就是这个电流 J 呢，必须是我们指的是它穿过去的正交于那个蓝色框框、蓝色的这个观察窗的这一个电流才有算数。Okay. Alright, so let's use the Ampere's circular law in integral form. That is, the closed loop integral of magnetic field intensity H equals to the time derivative of the surface integral of the electrical flux density plus the surface integral of electrical current density J. If epsilon is finite, when the blue rectangle is compressed, I mean the delta Y is reduced. If delta Y is reduced to nearly zero, then the total electrical flux passing through this blue rectangle will approach to zero. That's the reason why we say when S goes to zero, the total electrical flux passing through this region, this blue rectangle, goes to zero as well. Okay, so if we compress the blue rectangle into a very thin strip, we will end up with just two terms. The left-hand side, the closed loop integral of H, can be divided into four terms. That would be C1, C2, C3, and C4. As you can see, for C2 and C4, the length of Y delta dy will approach zero if the blue rectangle is compressed into a very thin blue strip. Then we will have only the first and the third term on the path C1 and C3. That will be the line integral of H1, that is underneath the interface, and the line integral of H2 above the surface on the two sides of the interface. And they can be non-zero. The sum of the two terms of the two line integral can be non-zero if and only if there is a surface current passing through this blue rectangle. Okay, only the surface current can exist, can be non-zero when you compress the blue rectangle. So the original Ampere circuitial law in integral form can be reduced to this if you have a very thin blue rectangle. The H1 and H2, I mean the magnetic field intensity below and above the interface, we only account the so-called tangential magnetic field, because as you can see here, the line integral process will only account for the components of H1 that is tangential, is parallel to the interface. So you have a inner product over here, the dot product over here. So you only account the component of H1 that is in parallel with the x direction. And you also account only the components of H2, the component of H2 that is in parallel with the x axis. On the other hand, the surface current J, you only account the component that is perpendicular, that is normal to the blue rectangle. So this is the x-axis, this is the y-axis, so you only account for the z component. So that's the reason why on the right hand side of the equal mark you have JIS.z, okay? And if you remove the delta x, the length of the rectangle, you end up with this. H1 minus H2, the difference between the magnetic field intensity across the interface, dot x equals to JIS.z. And x can be replaced with the cross product of y cross z. So by doing this, the equation can be further simplified. The dot product of z can be removed, so you end up with H1 minus H2 cross y minus JIS, the surface current in the z direction, and you have H1x and H2x cross y. Okay, so you actually account only the tangential component of magnetic field intensity above and below the interface. So this means the tangential component, the difference of tangential magnetic field components equals to the surface current densities on the interface. So here we goes. The relationship derived in the previous slides can be further simplified like this, and this will be the most general case if you replace y as n, okay, with the normal vector of the interface. So if the surface current equals to 0, then there will be no difference in the tangential part of the magnetic field intensity across the interface. 如果表面电流为0，则界面两侧的 tangential 的 magnetic field intensity 的 tangential component 是相同的。所以注意到，安培电路定律只告诉我们界面两侧的磁场强度的 tangential component， OK， 它只告诉我们 tangential component 哦。你只要知道磁场强度的 normal component 的话，你要再去用 Maxwell equation 的另外一个关系啊，另外一条 Maxwell equation 哈，所以我们有4条 Maxwell equation， 所以它会告诉我们电场跟磁场的 tangential component 跟 normal component 啊，所以我们这边一开始我们只看到磁场的 tangential component。OK， so we have 4 Maxwell equation, then we will have 4 boundary condition relationship that will be the tangential and normal component of electrical field intensity and magnetic field intensity across the interface. So here is our first result, first boundary condition. Tangential magnetic field intensity can be discontinuous across a boundary if and only if there is a surface current on the boundary. If you have a surface current on the boundary, you have a discontinuity in the tangential component of magnetic field intensity. On the other hand, if you have no surface currents on the interface, then the tangential component of magnetic field intensity across the interface in medium 1 and medium 2 should be the same. Okay? So remember to look into this red box a couple of times. Next, we can look into the Faraday laws. That's the second boundary condition. We will look into the tangential component of electrical field intensity across the interface. According to the modified Maxwell equation, that is the Faraday laws. We will use the same technique. We'll end up with the tangential components of electrical field across the interface. That will be the difference between E1 and E2, and not that the cross product here extract only the tangential component, and they should be equal to the amount of magnetic surface current on the interface. However, as we know, there are no actual magnetic currents. So, in general, the tangential electrical field intensity should be the same across the interface. So here is our conclusion. Tangential electrical field intensity must be continuous across a boundary because there is no surface magnetic current on the boundary. Well, that's the general case. Okay. Later we will discuss some special case. So when you try to devise, say, a solar antenna, 操孔天线, you kind of cut a slot on a metal surface like this. Then the fields built on the slots can be represented as magnetic current, and then you will have the so-called tangential electrical field on the solar region. Okay. All right. So next, let's move on to the third boundary condition. We will use Gauss's law of electrical field. So as you can see here, this is the integral form of Gauss's law of electrical field. The left-hand side is the closed surface integral of electrical flux density, while the right-hand side is the volume integral of electrical charge, which means the total charge confined in this closed surface, 也就是这一个封闭面里头所包含的电量总和。Okay. So if you draw this condition, you will kind of have a box placed at the junction of two surfaces of the surface between medium 1 and medium 2. And similarly, we will compress this cylinder. Okay, we will reduce the height of this cylinder. So delta y approaches to 0, which means the closed surface integral, the original closed surface integral includes the d going out of the top surface, going out of the bottom surface, and going out on the side of the cylindrical surface. When delta y approaches to 0, we only need to account for the electrical flux going up and going down. So you are kind of extracting the normal product, the normal component of D1 and D2 at the interface. Okay, so you have the left hand side is the difference between D1 and the normal component of D1 and D2, and the right hand side will be the surface charge reside on the interface between medium 1 and medium 2. So that will be the surface charge density. So the surface charge density is written as rho ES, electrical charge on the surface. So when the delta y approaches to 0, which means the cylinder becomes a planar disk, then you will extract the left hand side will be the normal component, the difference in normal component of D2 and D1, and the right hand side will be the surface charge on the interface. The physical interpretation of this equation is that normal electrical flux density can be discontinuous across a boundary if and only if there are surface charge on the boundary. On the other hand, if there are no surface charge on the boundary, then the normal component of electrical flux density across the interface must be continuous. 所以有表面电荷的话，那你的 normal component 电通量密度的 normal component 可以不同，两边可以不同。但反过来讲，假如你没有表面电荷的话，电通量两边的电通量密度的垂直分量就必须要相同。Okay, so we can derive the force boundary condition, and this is comes from the Gauss's law of magnetic field. So similar to the Gauss's law of electrical field, we can extract the normal component of magnetic flux density, the difference across the interface, the difference in normal component in magnetic flux density must equal the amount of magnetic charge density at the interface. So as you know, there is no real magnetic charge. So the right hand side of this must equal to 0. So the physical implication of this relationship is the normal magnetic flux density must be continuous across a boundary because there is no magnetic surface charge on any boundary. 所以这边我们就推导完4个 boundary condition， 从4个 Maxwell equation 推导出4个 boundary condition. Next, we will examine a special case, which is commonly seen when it comes to wave propagation. That is, if one of the material is metal or a perfect conducting electrical conductor, which is usually abbreviated as PEC, perfect electrical conductor. So assuming that medium 1 is PEC, then what happens about the boundary condition? So we are looking at the boundary condition at metal surfaces. One fundamental about PEC material, perfect electrical conductor, is that there is no electrical and magnetic field within the conductor, within the good electrical conductors. We know this is related to conductivity, which means the conductivity within the perfect electrical conductor is infinite. I know you should have heard the so-called skin depths. It's described that some electrical and magnetic fields can penetrate within a electrical conductor. Okay, but the thickness of the presence of electrical and magnetic field intensity is inversely proportional to frequency, inversely proportional to the conductivity of the material. So for perfect electrical conductor, that is, the conductivity goes to infinity. The skin depth will goes to 0, which means no electrical field and magnetic field intensity can survive within the perfect electrical conductor. Okay, so bear this in mind, that when it comes to PEC, there's no electrical field, and there is no magnetic field within the region of PEC. So we only have electrical and magnetic fields on the other side, medium 2. Okay. All right. So let's begin with Faraday's law. The first relationship here is the tangential components of E2 and EY. The difference in tangential components of E2 and EY equals to the surface magnetic current. And because there is no E1, there's no electrical field intensity within the metal, we only have tangential electrical field in medium 2. So you have N cross E2 equals to minus of magnetic surface current. And back to reality, we don't have real magnetic surface current. So MIS goes to 0. Then we have this result, this important result. On the surface of a metal material, on the surface of a good electrical conductor, there should be no tangential electrical field. Okay, so no tangential electrical field on metal surfaces. Okay, so because there's no magnetic current, there's no tangential electrical field on a metal surface. Okay, the second boundary condition about PEC, because the electrical field and magnetic field are coupled for time varying electrical magnetic fields. So for electromagnetic wave, the electrical field intensity and magnetic field intensity are coupled. They cannot survive alone. So if there is no electrical field intensity, then there is no magnetic field intensity. Okay, so because there is no electrical field intensity, the electrical field within the PEC material within medium 1, you have no magnetic field within medium 1 as well. So H1 goes to 0. H1 goes to 0. This is the now we are looking into the tangential part of magnetic field. And so therefore the left hand side is the difference of H1 and H2, the tangential bar of H1 and H2, and the right hand side is the surface electrical current density. So because H1 goes to 0, because this is PEC, so you have the tangential component of magnetic field must equal to the amount of electrical current density, J. So as long as there is an electric surface current on the metal boundary, on the metal surface, there is a tangential magnetic field on the metal surface. 所以只要金属表面上只要有表面电流，那就表示你有 tangential 的磁场。Okay. All right. The next thing is the normal component. Okay, so we are looking into normal component of electrical field and magnetic field. So here, if we have this is our original relationship. The normal component of magnetic flux density equals to the amount of magnetic charge density on the interface. And of course, we know that there is no magnetic charge. There is no magnetic charge. And because on medium 1, in medium 1, which is PEC, you don't have magnetic field intensity, you don't have magnetic flux density as well. So this is reduced to N dot B2, that is the normal component of magnetic flux density on the other side must equal to the surface magnetic charge density. And because you know that this one goes to 0, you cannot find a magnetic surface charge on any surface. So the normal component of magnetic flux density on the surface must equal to 0. So because there is no magnetic charge, there is no normal magnetic flux density on a metal surface. Okay, again, this applies to metal surface. 所以你没有磁场，没有垂直分量，金属表面上没有垂直分量的磁场，没有 tangential 分量的电场，没有垂直分量的磁场。然后，只要你有表面电流，你就有 tangential 分量的磁场；只要你有表面电荷，你就会有 normal 分量的电场。这个我们在下一页会看到。Okay, so the very last relationship about boundary condition is the normal component of electrical flux density. So from Gauss's law of electrical field, we know that the normal component of the difference of D2 and D1 equals to the charge density placed on the surface, placed on the interface. So as long as low ES is non-zero, then the normal component of electrical flux density D2 can be non-zero. Can be non-zero. So as long as there is an electrical surface charge on the metal boundary, there is normal electrical flux density and normal electrical field intensity as well on the metal surface. 所以金属表面只要有电荷分布的话，表面电荷分布的话，就会有 normal component 的电磁场的电场跟 normal component 的电通量。So here is the summary on the PEC boundary. The surface currents will produce tangential magnetic field. The surface charge will produce normal electrical flux density. So the second one, the magnetic current density M, magnetic current density, if it exists, then you can produce tangential E field on the surface. This is what we do when you design a slot antenna or a patch antenna, the so-called magnetic type antenna. The magnetic type antenna try to introduce a tangential electrical field on the surface of on a metal surface. Let me explain this. So if you have a large metal surface and you cut a slot on it, and if you can apply an electrical field across the slot, okay, that's the only way you can have. So you see, this electrical field is the so-called tangential electrical field, right? So this tangential electrical field is equivalent to magnetic current. Okay, now N cross E, so you can see that the direction of E is this. So if you do the cross product, N across E, well, actually, not this way, it's this way, okay. You will end up with a magnetic current. Oh, I'm sorry, okay. So the magnetic current is still because of the negative sign, okay. So anyway, you will end up with an equivalent magnetic current on the aperture, of the electrical surface, okay. So similarly, if you can induce normal component of magnetic field, you will produce the equivalent magnetic charge. Okay, so even though we don't have real magnetic current and real magnetic charge, it can put equivalent magnetic charge and equivalent magnetic current can be produced by according to your own design. All right, so that should conclude our first chapter in electromagnetic theory.